We will now begin to understand the complexity of certain molecules, and these molecules are called as organic molecules. The term organic does not mean that these are present only in the earth. They're grown from the earth, or they're just pertain to the vegetables or the fruits that you see. There's a range of organic molecules, but we in general are looking at the organic molecules that are present in living organisms. So, what are organic molecules? The answer to this is they must all contain the element carbon. Carbon is one of the elements that you will find in the periodic table, and organic molecules are molecules that have carbon. The definition that you will hear in many chemistry classes is organic molecules do not have to do with just living matter. In other words, there are organic molecules that are present that are not associated with living. But in this particular section, we are only looking at the four types of organic molecules that are present in living organisms. And these are, and in no particular order I'm writing these names. The first one is the carbohydrate, which maybe you're familiar with. Most of us are. Proteins. Think of the diet that is heavy in carbohydrates. Think of the diet content that is heavy in proteins, lipids, and the last macromolecule is the nucleic acid. Now, the term macro means large and big, and these molecules are very big and humongous, and that's why they're called as the macromolecules. Now, except for the nucleic acid, the first three are present in our diet, and we do take them in all kinds of foods and meals that we consume every day. Why is carbon so essential to be present in all organic molecules? If you go back and look at the periodic table, you will find carbon has the number 12 written over here and 6 there, which means that it has 6 electrons in its shell. Now, if you recall, I did give you previously how the electrons were arranged. The first shell can hold 2, and the second shell can hold 4. So if that's the configuration of electron arrangement for carbon, then if you recall from the previous section, we also talked about some vacancies in the shell, and the vacancy, the number that the shell can hold maximum is 8. So if 8 is the maximum number, you can see that there's a vacancy of 4 electrons. Now, these electrons that are needed can be formed by sharing of electrons between carbon and another atom, which results in 4 bonds that it can form. Now, these bonds that carbon can form can be either single. Notice I wrote 3 next to the hydrogens because there are 3 hydrogens that are filled up, and a carbon-carbon bond. If I place 2 double bonds here, then you can assume that there will be 2 hydrogens on each side. And if I have 3 bonds, then there will be 1 hydrogen on each side. So these are single, double, and triple bonds that carbon is capable of forming at different stages or different units. Another very important feature for carbon is that carbon can keep on forming long continuous chain. In other words, if I was to erase the hydrogen over here, let's get my eraser out. If I was to arrange this hydrogen here, I can connect this to another carbon and then connect the other hydrogens or carbons and so forth. So doing this continuous stage, we can see that carbon can form very long chains. All right, let's go on to the next slide. So, present that I just showed you. Now, Let me actually tell you something up here that I missed out. The macromolecules that each one of them is composed of. A macro means large molecules, and these large molecules are formed by chains of smaller molecules, and these smaller molecules are called as the monomers. Mono means one, mers is a unit. So literally the word implies that the chains of these units of each mers or the monomers are put together in longer chains, and these chains that are forming are going to be formed either of a carbohydrate, lipid, or a protein or nucleic acid. All of them will have the same principle of forming these continuous chains. And so regardless of the monomer that I will give you, for each will be a different monomer. Let's look at the generic scenario of how a monomer will connect. Each monomer would have a hydrogen on one end and an OH of the other monomer, will then form the water molecule. The water molecule is actually more like a waste. It's generated, and when the generation of one water molecule will link these molecules on these ends together as a new bond. So this would be a reaction in which you're synthesizing or connecting each unit. So monomer plus monomer will give you one water molecule, and the chain that you get is called as a polymer because they are more than one. You can call them polymers or chains. Now the opposite of this would be hydrolysis. Hydrolysis means that you use water to break the chain. So each of the polymer plus the water is going to split that particular. So here's my chain again. If I use my water molecule, again what's happening is it's splitting and releasing a hydrogen to complete the charge, the valency on this monomer and the OH on the other. So both of these reactions are important because one is synthesizing larger macromolecule and the other one is breaking it down. We need the synthesis usually when you're trying to build up larger chains of proteins or chains of lipids or chains of nucleic acids during synthesis of DNA or chains of carbohydrates. Now lysis literally means split. So you're saying that water is used to split the molecule. Now this would be a generic scenario that you will see in all the different macromolecules. For each macromolecule, however, I will give you the monomer that is required to connect the two units together. Something else about the functional group. Functional groups, here is actually a list of all the different functional groups. Those of you who have had chemistry before may be familiar with some of them. Hydroxyl is this OH group. Here is a group that is called as aldehyde. Here is a group that is called as ketone. Here is a carboxylic group. There is an amine. Here is thiol, and there is a organic phosphate. Now all of these groups are pretty much present in many organic compounds that are around you. Whether it be your clothing, your furniture, the paint around you, plastics, styrofoams, synthetic drugs, pharmaceutical medication, full of functional groups. However, some functional groups are hydrophilic and some are hydrophobic. Hoping you'll remember the term philic. Philic is water loving. So those groups that have the oxygen, hydrogen, or they have a polar consistency. For example, you can see hydroxyl groups are polar, carbonyl groups are also polar, carboxylic groups are also polar, amines are also polar, phosphates polar, sulfhydryls polars. So these are this particular chart has listed only the polar groups. There are other non-polar groups, for example, alkanes, alkenes, and some of the others that you really haven't done, amides and so forth. Those are the hydrophobic groups. Anyways, we'll not go into those, and I don't expect you to know the names of each group, but know that this is a unique combination of carbon in each of these in this class. You can see how they're arranged differently. And another very important characteristic that's present in carbon compounds are that they're isomers. Isomers are compounds that have the same number of carbons, but they have two different names. For example, if you look at this one, if I count the carbons, I have 1, 2, 3 carbons. If I count carbon here, I also have 3 carbons. If I count the number of hydrogens, I see 1, 2, 3, 4, 5, 6. And let's count the number on this one: 1, 2, 3, 4, 5, 6. And they have one oxygen. No, it actually has 2 oxygens here. And this one has, no, it has 3 oxygens. I've got 1, 2, 3. 1, 2, 3. So notice that if I write down the molecular formula, they're exactly the same. But there are 2 different names given to this compound. And that's because they're structurally different. If you look at the way the oxygen is shown over here, the carbonyl carbon, you can see that it's in the middle in this particular case, and it's more in the end. So these are another very unique combinations of functional groups. Functional groups are they have their own properties, and if you were to take a chemistry class just for understanding, you will find it's going to be very intense. So we'll stop this section over here, and then we'll go on to the next section.